Hi, this is Dr. S.P. Harsa from Mechanical and Engineering Department, IT Roorkee. I am going to deliver my lecture 32 on the course of the strength of materials, and this course is developed under the national programs on technological enhanced learning. In this lecture, we basically are going to discuss about the alternate deflection method, because in the previous lecture you see we discussed about the main method of the deflection, that if a beam is subjected under the various kind of loadings, and due to that if the deflection is there, then first we discussed in the previous lecture about the beam deflection theory, that under certain assumptions, like you see whatever the deflection is there, it will follow the Hooke's law, and the stress is proportional to strain. And the second assumption which we made, that whatever the deflection curve is which we are getting, it has to be very, very small as compared to the main deflection curve, so that we can say that whatever the streamlined or the central axis is there of the beam, it has to be remain in a particular limit, then only we can say that this theory whatever we developed is applicable. And the third thing, actually we assume that whatever you see the deflection is there, mainly it is due to the bending, the shearing effect we are always trying to ignoring. So with those three assumptions, we derived one equation for a basic deflection theory in the previous lecture, that was equals to that was equals to m d2y by dx square is equals to this m, or m divided by ei. So with that we found that this all moment with this rigidity, the flexural rigidity is always be compared. Now with that you see if you have the this bending moment m, which is equals to ei into d2y by dx square, we can also found that we can easily get the shear forces, or we can get the rate of loading, or else also we can get the slope. So the slope as well as the bending moment as well as the shear forces and the rate of loading, they are pretty symmetrical with those differentiation. So we found that they are all associated with, like if we are talking about the slope, then it was d2y by dx square. If we are talking about the bending moment, then it is a second derivative, that d2y by dx square. And if you are talking about the shear force, that was nothing but equals to dm by dx. So it is the cubic form, and then the rate of loading, which is nothing but equals to this w, which we are taken generally in our notation, which is equals to df by dx. So we have the fourth order of the derivative. So in all of the sequence, we found that they are the somewhat multiples of the differentiation of these deflection, because you see here we are taking the deflection in y axis, and on x axis we have the longitudinal axis of a beam. So with that consideration, we found that if you have an integration method, then it's pretty easy to find all those quantities in a sequential way. So with that concept, you see the first method which we applied for the deflection theory of beam is the direct integration method. And then we found that it depends on the boundary condition, we can get easily the deflection for a beam. So you see here in previous lecture, if you focused, then we discussed 4 different cases with respect to deflection. So first case which we discussed, that if we have a cantilever beam and the point load is acting at a free end, then what has happened? Then you see we applied that the maximum deflection and maximum slope will come at x equals to 0. That means you see at the free end where the point load is acting. So with those boundary conditions, you see, and there is no slope and there is no deflection is there at the rigid end, where you see the rigid joint is there between the beam and the rigid support. So with those boundary conditions, we found the generalized deflection and generalized the slope expression. And then you see after applying those conditions for maximum and minimum deflection, we get the maximum deflection as well as the maximum slope. So that was we discussed for the first case. And similar you see the conditions we got for when this cantilever beam is there and UDL is there. Instead of point load at the extreme end, free end, we simply applied this time the UDL, and then you see we observed the similar kind of expression for the slope as well as the deflection criteria. And then you see again we applied the similar the boundary conditions for the cantilever, because certain constraints are there in those things, and then you see we observed the maximum slope and maximum deflection at the free end also. So these two cases we discussed about the cantilever beam. Then you see the followed these 2 cases which we discussed later part, that was you see simply based on the simply supported beam, in which you see in the first case we discussed about when a UDL is there, which is spread all across the span of this cantilever beam, and simply the supports are there at the extreme 2 corners of that particular beam. Then how we can put those boundary conditions on that particular beam, and how we can get the deflection as well well as the slope expression. So that you see, that part we discussed, and we found that at the center point, because in the cantilever beam we got the maximum slope as well as the maximum deflection at the extreme corner where the free end is there. It's quite obvious, but here in this case, when a UDL is there, there is no other loading on a simply supported beam, then we found that the maximum deflection is coming at the center point of a beam, and at these two extreme corners where the support reactions are there, there is no deflection at this point. So with that conditions, you see, we observed the maximum deflection as well as the maximum slope value, as well as we observed the expressions for the slope as well as the deflection one. And then last case which we discussed, that actually if we have this simply supported beam and the point load is there which is not exactly at the midpoint, which is somewhere at this distance from we assumed the previous case that we have a distance from this left hand side, from left hand reaction, and we have a b distance, and a and b are not equal. They have a big difference in terms of the distances, but a plus b is the total length of the beam. So with those cases, we need to apply, and we have some sort of bulky this equations for this kind of this simply supported beam with this kind of loading. Then we apply the similar conditions for one portion AB and one portion BC. Then we obtained, and we found that actually wherever the point load is there, at those points the deflection as well as the slope is equal. So by putting that condition, by assuming that condition, we obtained certain the value, and then also we got that what will be the value of this maximum value of the deflection as well as the slope, and also we describe those expressions for that. So these four cases which were very important as far as the deflection of beam is concerned, we discussed, but with the same method, the direct integration method. But we found that in some way it is very bulky. So we observed that actually we need some alternative methods to describe this kind of condition, because sometimes the loading is not simple. It is not because of the point load, or it is because of the UDL. If we have a combination of load, or if we have along with the loading, if we have the additional couple or twisting moment is there, then how we could find out those things. So here in this lecture we are going to discuss about the alternative methods for to calculate the deflection for this kind of beams. So first in the fourth case which we discussed yesterday, again if a point load is there at the center position, then how we can go for the alternative method. So here here the alternative method is, there is an also alternative way to attempt this problem in a more simplified way, and let us consider the origin at a point of application where the load is there. So that's what you see. If you see on your the diagram on your screen, then you'll find that we have a simply supported beam, and these two reactions are there because you see here the point load is acting exactly at the center point. So due to that, we have the reaction forces extreme at the two extreme corners equally, and they have the magnitude of W/2. So with that W/2, you see these at both of the corner W/2 here, and the W at the center position. Now what we are going to do here, we are not going for the similar pattern which we observed in the previous way. Here what we are doing here, we are simply taking the x-axis cutting this beam at x-axis section. So here you see this is our x-axis section, and then this is the total length of beam is there, and since this load is applied at L/2 at the midpoint, so this is L/2, and if I am saying that this is x by x section, so obviously you see from this distance we have the x. Instead of using the previous cases, we have taken the x distance from the reaction part. Here we have taken the x distance from this load application, because you see the load application is the main criteria here for the deflection, because these are the originating for any kind of deflection in the beam. So we need to focus that actually where this point of load is there, and then how we just want to see that how the variation is there. So for that actually we need to put the section with respect to this point load. So with that consideration, you see we simply cut this beam at x-axis section, and it has a distance of x from this load, and then obviously since this is L/2, so this distance is quite obvious, L/2 minus x. So with that, now you see here we are going for the similar pattern, that first of all we need to find it out the shear forces, and for that you see the shear force is nothing but equals to W/2. And again you see as far as the sign conventions are concerned, since you see I just focused on the left hand portion of this particular, you see on this screen this portion, so here you see the reaction forces are going on upward side, the load is there on downward side. So with this particular loading condition, shear forcing we have a positive sign, so shear force at x-axis action is obviously W by 2 due to the reaction. And then you see, like we can also calculate the bending moment, and again if you are going for the bending moment sign convention, then it is, you see, like the point load is there on the beam, so it is just going like that. So this is kind of a sagging position. So for sagging position, again you see we have a positive this bending moment is there. So bending moment at x-axis action also, it is mainly due to this reaction forces. So we have W by 2 into L by 2 minus x, this is the distance. So for this, you see, like we can simply consider the shear forces as well as the bending moment. So now with the consideration of, like the shear forces and bending moment, go with the, like the main equation of the deflection, that is m is equals to ei into d2y by dx square. Put those values here in that equation. We have d2y by dx square is equals to, this is bending moment m, W by 2 into L by 2 minus x divided by, like these whatever the reaction forces are there. So ei is the flexural rigidity. It is a material property, as I told you first, that what is the Young's modulus of elasticity is there, because here whatever the deflection is there, as we already assumed that it is under the elastic deflection. So you see whatever the stress is there is proportional to strain. So E is valid for these things, and then I is based on, like the mass moment of inertia, or we can say the second moment of area, which absolutely depends on what the cross section of the beam is. So we can calculate, if we have, like the rectangular cross section, then we already discussed that it is BD cube by 12. So with those things, you see, like we can simply get the d2y by dx square with those things. Now if we integrate those things, we have dy by dx, that is the slope. Slope is nothing but equals to, like 1 by ei w into L by 4 w into L into x divided by 4 minus wx square by 4 plus one constant a, that is the integration constant. And then again if we integrate, then we have the deflection term, that is equals to 1 by ei w into L into x cube divided by 8 minus wx square by 12 plus ax plus b. These are, like the simple, like the constants are there for the integration, and by keeping, like this is a simpler method, because what we are doing here, instead of going with from the left hand side, we simply like taking the distances from the load, so that if any variation is there in the load, the distances can be easily calculated and incorporated in this particular expression. So now you see here with those things, again we would like to put certain boundary conditions to get the value of the deflection as well as the slope, so that you see, like a and b can be easily calculated. So with that, you see, first of all, at x equals to 0 there is no deflection, there is no slope. So with that, because you see it is a simply supported beam, so wherever the reaction forces are there, they won't allow the beam to having any kind of slope, because they are providing a rigid support at those points. So with that particular physical concept, here again we are applying here that at x equals to 0 or at x equals to L, we have dy by dx equals to 0. That means the slope is 0. So if you keep that x equals to 0 in first expression where dy by dx we calculated, only the coefficient a was there and it becomes 0. Then we have, like one coefficient a is 0. Now at x equals to L by 2, the middle portion where you see, like we are putting the point load. So when we are putting the point load, obviously that slope will be 0, the deflection will be 0. So we have y equals to 0. Then like because now L by 2 is on the left hand side or right hand side of the support, it is exactly at the middle of the portion. So we can simply say that this is the origin where, like the deflection, and this is the origin where the deflection will start. So at this particular point where x equals to L by 2 is there, that means where the point load is there, we can simply put y equals to 0, and then we can calculate those b values. So you see here, by keeping that at x equals to L by 2, y equals to 0, so the y is equals to 0, and like it is 0 is equals to, because it was the y expression deflection equation, so y equals to 0, 0 is equals to wl cube by 32, because here we simply put x equals to L by 2. So you see now x is totally replaced by L by 2, so we have wl cube by 32 minus wl cube by 96 plus like the b coefficient, because we want to calculate this b, so we have minus wl cube by 48. So now you see we have the a value, we have the b value, so we can put those a which is 0, b which is minus wl cube by 48. We can keep those values in the final expression of the deflection, and we can get the real feeling about the deflection, that how the variation of the deflection is there in the beam when a point load is applied on a simply supported beam exactly at the midpoint. So you see here, by keeping those values a and b, we have y equals to 1 by ei wx square by 8 minus wx cube by 12 minus wl cube by 48. So now you see here, we have a clear feeling that this deflection is varying in those like due to the point load is in a cubic way, because you see, you can see that the total dimension in all of the expression is x square into 1. So it is total cubic form, this is cubic form and this is cubic form. So the variation is there in the cubic form, irrespective, you see, you can put the value of x in terms of the L and you can get the different deflection at different points. But now our main intention is to find out the maximum deflection, and always you see when we are putting those point load at the center, we have the maximum deflection. So by keeping at x equals to L by 2, we have the maximum deflection value. So you see here at x equals to 0, if we are keeping, because now we are reducing the x, whatever the distances were there in between the x, we are simply going up to the L by 2. So here you see, if by keeping those things, what we have, minus WL cube by 48 EI. So you see, by this x is gone, this x is gone, so we have only this value. So this value is nothing but equals to minus 48, this minus WL cube by 48. So we have, and into this EI is there. So this is the maximum deflection is there. And then you see, if you want to find it out, the maximum slope, obviously they will be there at this point particular. So you see, if you are keeping that x equals to L by 2 plus minus, you see where the maximum slopes are there, the center point. So by keeping those values, we have, you see, at x equals to L by 2 here we are keeping, and then if we manipulate those things, we have the final value is plus minus WL square by 16 EI. So meaning is pretty simple, that one can easily get, this is a very simple method as compared to the previous one, because here in the previous cases, we what we are doing here, if if we don't know those distances, that actually at what point these loading conditions are there, then what we need to do here, we need to take the x distance from the left hand portion, that means you see from the reaction forces. But instead of that, you see here it is pretty simpler to take the distance from the loading condition, so that if any variation is there in the point load, it can be easily calculated. So this is, you see, the alternative method. But again, you see, in both of the method, the direct integration method, you see, in one form or other, there are certain discrepancies are there. So you see here, hence the integration method may be a bit cumbersome or bit bulky, because you see, again, you need to describe, you see, for all the expressions, for even the slope or for deflection or for shear forces, kind of that. So in some way, you see, you will find that we have a bulky equations, the cumbersome equations are there, and then if we have the kind of this stepped bar, you can see on your screen, if you have the non-uniform cross section of the bar, these stepped bars are there, you see, then it is pretty horrible to analyze all those things for different sections, because you see, for individual sections we have a different equations, and for that, you see, then again you need to sum up. You have a very cumbersome equations, or we can say it's a very bulky or lengthy equations are there. Then again you need to put the boundary conditions for those things, which is very complicated. And if you see, if any other kind of loading is there on this kind of beam, then it is really desirable, disaster is there to calculate those deflection as well as the slope value for this. So what we need to do here, we need to go for alternative methods. So there are, you see, the three methods are available, in the solid mechanics theory for undergraduate courses, that which we can simply apply for this kind of beams, or even for simpler beams also. So one method is the Macaulay method, in which we can simply write the different equations, whatever you see, those equations are coming for bending moment for a different section. So what we are doing here, instead of going for an entire beam, here we are simply taking the individual sections, and then you see, just write this equation, apply this boundary conditions, and get those values. So Macaulay method is very much suitable for this kind of sections, where you see the different in a particular total beam, if you have a different stepped sections are there, or non-uniform sections are there, then this method is quite applicable. But that doesn't mean that actually we cannot apply in a simpler beam also. We can also apply the simpler beam to get the value of those the deflection as well as the slope. Second method is there, the area moment method. So in this chapter, basically our focus will be there on the area moment method, that you see, we have a bending moment, and you see under the bending moment diagram, we have certain, the diagram is there. So if you, because the loading conditions are there, and whatever the cross section of the beam is there, they will definitely go with the kind of specific bending moment diagram. So our focus will be there, that actually what will be the area under that diagram, and then based on that, you see, we can simply find it out that okay, now this much deflection is there, or this much slope is there on those things. So it is basically based on the area with the moment method. So whatever you see the bending moment is there, and whatever the area is coming under those things, based on that we can calculate. So we'll discuss this part, this particular method in this lecture. And third one is there, the energy principle method, that you see, like when you apply the load, definitely you see some sort of the energy exchange is there in terms of the potential to kinetic energy. So if you compute those potential and the kinetic energy in some sort with using Lagrange's method or any other method, we can simply go that, like here you see the kind of variations of the energy is there. So we just want to relate the energy with the deflection, and then we can go for the slope also, and we can also find out that actually at what positions or what are the potential the areas are there where the maximum deflection or maximum slopes are coming, and what will be the value of those things. So these three methods are there which have which will provide some sort of a different methodology as compared to the direct integration. Though you see, like for academia purpose, the direct integration method is quite simpler, because you see once you know that okay, this d2y by dx or d cube y by dx cube or d4y by dx4, so we can calculate simply all those values like slope or deflection or like these bending moment, shear forces, or like the rate of loading. So these that's why you see this method was in academia. This method, the first method which we discussed, is quite popular. But here you see, like the second method which we discussed, that area moment, or like the moment area method. Anyway, you see, like it's just the similar kind of manner. The area moment method is a semi-graphical method, because as I told you, we are simply focused on the bending moment diagram. So it is a kind of, you see, first we need to focus on the diagram and then we need to calculate. So it is not purely graphical, but it has some sort of feeling about the graphical interaction with the mathematical way. So it is a semi-graphical method dealing with the problems of a deflection of beam subjected to bending. So you see here, like if any kind of beam is there, simply supported or cantilever beam, and when any loading is there, sort of bending is there, and then you see we need to focus with the kind of reactions and the load application, that what the boundary conditions are there, and then once you draw the bending moment diagram, you have a clear feeling that okay, now you see these, like these are the portions where the maximum bending moments are there, these are the portions where the minimum bending moments are there, and based on the area under that particular diagram, we can calculate the deflection. So this method is based on the geometrical interpretation of a definition, this definite integrals, as I told you, and this is applied to the case where the equation for bending moment is to be written in cumbersome, and we can say that means if the bending moment equation, as we discussed, you see m is equals to like ei into d2y by dx square. If you go for a lengthy equation or for longer equation, this method is quite popular in those cases, and loading is relatively simple here. Let us recall the figure, you see, like which we discussed in the previous case, which while deriving, like the differential equation for governing equation, like m is equals to ei into d2y by dx square. So again, if you go back to that equation, you see here what we had, like under the any kind of loading, a kind of, like this the central axis or longitudinal axis of the beam is having certain kind of deflection. So as I told you, when there is no loading condition was there, then we have a straight, like the central axis, that is the A to B. But if we have the loading condition, then you see this A to B is like changing into the A dash B dash, and we have a kind of a curvature shape is there. So in that curvature shape, again we describe that was the pretty, like the assumption was there that whatever the curve is coming, that curvature, this either deflection curve or the elastic curve, they have to follow the elastic deformation or elastic deflection terms. So that's why you see the deflection curve is also known as the elastic curve, as it is written here. So A dash and B dash is the deflected curve. In that you see the deflection is absolutely on the d theta. So here you see the the d theta is there, and if you take any origin which is the reference point from this curvature point, then we have these kind of that how much change is there when a straight portion and when a deflected portion is there. So d theta can be easily measurable. So if I am talking about a small segment, we have the ds in the deflection part, we have the ds is the deflection part, and dx is the straight part. So if I am talking about a small angle, like you see, like this tan theta, which we are taking the slope, this d theta by dx or ds by dx, whatever you see. So always you see the slope will be, make the clear difference in between the ds and dx, because you see the slope will come for dx, there is no slope here. But if the slope is very, very small, as we are generally assuming that the deflection curve is always these theories are applicable for a small deflection curve. So for that kind of section, you see the ds is almost equal to dx. We'll discuss this part, it will come, and then you see we have the theta, that how much deflection is there from the main axis in the longitudinal way as compared to that. So you see here, this is the longitudinal axis, we have the theta, or we can measure in this way also. So this is a clear feeling about the deflection curve, which we discussed in the first method, direct integration method, and here also we are using the similar kind of concept here. So Here in that we just noted that d theta is the angle subtended by like the arc element with the ds, and m is the bending moment to which this element is subjected, and due to that bending moment you see we have the deflection in that particular beam. So just go to the equation. We have the arc equation that r theta is equals to ds. So d theta by ds from this equation, because this is a pretty simple curvature theory is there, that if you have radius of curvature r and any angle is there d theta, then it is exactly equals to r into theta will give you the ds. So d theta by ds is equals to 1 by r, and if you go to the main bending equation, then we have this m by I is equals to sigma by y is equals to this e by the r by e. So you see here with those, you see if you manipulate those equations, we have m by I is equals to e by r. So 1 by r will be equals to m by ei. So now we can simply replace this 1 by r is equals to 1 by this m by ei. So we have d theta by ds is equals to m by ei. So now with that, if you are going for the slope, that is the slope is there in terms of the dy by dx, which is equals to tan theta. And if I am saying that the theta is very small, so tan theta is equals to theta, so we can say that theta is equals to dy by dx. And now if we are going for the main this deflection equation, which is d2y by dx square, which it is giving that m by ei. Now if I am putting that those values, then we have since as I told in the previous figure that the ds is the deflected part and dx is the straight part, but if the theta is very small, we can go for the ds is equals to dx, because it is a curvature part and this is the straight part. And if I am saying that this curvature slope is very small, it is exactly equals to, not exactly, but it is somewhat equal to the dx value. So ds is equals to dx. If I am keeping those values, what I have now, you see the dx will be coming here. So d theta by dx is equals to m by ei, and by keeping those values, we have d theta is equals to m into dx divided by ei. So what it concludes, we have a basic equation of the d theta. That means you see how much deflection is there of a small element like this one, in the deflection part. So this deflection which we can be computed with respect to this d theta, which is equals to m into dx divided by ei. So with that condition, you see again we would like to focus that okay, this condition is there which in which we have a d theta which is very much valid for m into dx divided by ei. But with that relation which we we just set up in the previous equation, it can be given in a very simpler graphical interpretation with the reference to the elastic plane, because you see these are all the elastic curves or the deflection curves are there of a beam, and its bending moment diagram is pretty simpler, because now our main focus is that once you have a deflection, then how it incorporated in terms of the bending moment diagram. So here again we have a simple case that we have a simply supported beam at the extreme two corners, and if we have this kind of non-uniform loading is there. Okay, this is UDL sort of you can say that we have a this distributed load is there on that. So with that, you see we have a deflection curve. So this deflection curve is like that, you see here. So these A and B points are the real deflection points are there. We can say these are the initial point of the deflection, and then you see if we put the tangent from A and from B, so these tangents are meeting at some point, that is the point where the centroid is locating. So if you just focus on the bending moment diagram, just a lower portion, we have this centroid position, and always you see we are measuring the centroid from one of the reaction forces in terms of x bar or y bar. So here we are taking the x bar distance from these things. So we have the centroid, and with the kind of variation you see here, we have the bending moment diagram in this way. So this is a kind of deflection is there in this particular beam. So as you can see here, this is the deflection curve. So it has a maximum value at the center position, and you see starting from the zero deflection at these two supports, they are coming in this way, and if you put the tangent, then you can simply locate the origin of those things. And these always will go for the arc, that actually how much what is the arc length is there in this particular kind of deflection curve. So with those things, if you projected on the bending moment diagram, what we have, this is this particular portion where the bending moment is there, this is the m. And if you are talking about generally we are taking the small segment, so if you are talking about the small segment dx from the x distance of this particular portion, then we can simply show that our main focus of the study is on this one. Once you get the real feeling of the bending moment as well as the shear forces for these kind of things, then you can integrate those things and you can get the real feeling of the bending moment, or we can say other this kind of stresses in this kind of bending. So here you see you have the deflection curve and you have the bending moment diagram, and they are pretty simpler, and they are giving you main kind of information that actually where the centroid is located and how these deflections are taken place if this kind of loading is there. So just focus on that particular figure. We have AB, as I told you, these two corner points were there of this portion of, you know, like, and they are pretty simpler portion, because you see this is the starting point, and if we are projecting those, you know, like the tangent at, then we have the new you know, like the points are there, A dash B dash in the previous figure, and wherever you see the A to A dash and B to B dash are meeting, you know, like there is a point, and that point where the intersection is there of these tangents, it is the origin point. So you see here we have a AO, that is the tangent drawn at A this, and BO is the tangent drawn at B. So with those things, you see, you know, like this O point was come, and once you plotted those that O point in the this bending moment diagram, we simply got that the centroid point. So AA dash is the deflection at A, as you know, like I told you that whatever the deflection is there, we are measuring with the tangent away from the tangent at B, while the vertical distance BB dash you know, like is the deflection at point B away from the tangent at A. So both are, you see, you know, like just we just want to find it out a real feeling that how the deflection will take place under this kind of loading. So that's what you see, we are going for the tangent, and then you see wherever these tangents are meeting, as I told you, the O point is coming. All these you know, like the quantities are further understood to be very, very small, because you know, like if it has a very large, then always it is going beyond that limit, then you see we have a permanent set of deflections, and then you see these theories are not at all applicable. So just, you see, keep this thing in your mind that whatever the deflection, you know, like they are coming in those beams, particularly under these loadings, they are very, very small, and they are just up to the limit of the elastic region, so that whenever you remove the load, it comes to its original state. Now you see, we assume that the theta is very, very small, so ds is almost equal to dx for any element in the elastic line at a distance x from B, and angle between its tangent will be definitely d theta is there. So d theta can be derived as we derived in the previous one, is equals to m into dx divided by EI. So with that, you see, you know, like this relation, we can simply interpret, you know, like that angle is nothing but the area, you know, like into dx. So you see what we have the area under that. So if we integrate those part, like we have d theta, which is m into dx divided by EI. So now you see, if you integrate that, we have the theta value, theta is nothing but equals to 0, you know, like right from, let us say, we have the limiting conditions for that integration into m into dx divided by EI. EI is a constant one for any kind of cross sectional of the beam with the material part. So we just taken this one out. What we have integration m dx. So now you see this m dx is nothing but, it will always gives you that actually what will be the area under that particular portion. So you see here, these deflections are coming due to the bending moment, and these deflections are varying with the dx distance. So m into dx will give you, you know, like the area under that curve. Just like you see, you just focus on the work done. What the work done is there, if you focused on any thermodynamic processes, we have the work done is equals to P dV. Okay, and you see, if you are talking about any process like isochoric process, isobaric process, any process in the thermodynamic processes, what we are doing here, we are simply drawing the PV curve, and you see, you know, like with that the constant volume process or constant pressure process, we simply draw the curve, and whatever the area is coming under that curve, which will give you the work done, because work done is nothing but equals to integration of P into dV. So same concept is here, we have the theta, which is integration of m into dx. The m is varying with the dx. So we can get, you see, you know, like the real feeling about those the bending moment if you know the this area, and then you see, you know, like this whatever the area is coming, if it is divided by EI, you have the clear deflection. So you see here the total angle theta between the tangent A and B, if let us say we are talking about point A and B generally in that particular figure. So from A to B, you see we have, you know, like m dx divided by EI, or we can say that 1 by EI is a constant one, so just taken out, and then it is A to B m into dx. Since the integral represents the total area, obviously you see we initially we have to talk, you know, like we need to talk about the small segment and then integrate for the entire section. So the total area of the bending moment diagram will give you the real feeling of theta, and hence we may conclude that the slope or the theta between the 2 points will be equals to 1 by EI into the area of bending moment diagram between the corresponding you know, like portion of bending moment diagram. But you see, you know, like, and that's what you see, it is very much valid for the stepped bar. If you are talking about this portion, means the non-uniform section, then another different section for another sections, just go with those, you know, like the portions, draw the bending moment diagram and multiply with 1 by EI for that particular section, then you see you have the slope, or we can say the theta for in between that particular section. So that's why you see this is the basic principle of the area moment method, that you can easily calculate the theta by equals to 1 by EI into integration between those point m into dx. So you see here, once first of all you need to calculate the shear force, based on that you need to calculate the bending moment. Once you have the bending moment, put that equation, take the integration and get the value of theta. Now let us consider the deflection at point B relative to the tangent A. So you see here, like we simply put the tangent, like at point B with respect to A. This is nothing but the vertical distance between the BB dash, obviously you see, which we noted in the previous section where the two deflection points are there. It may be noted that from the bending moment diagram, the bending of element ds contributes to this deflection by an amount of like x d theta. That means each intercept like may be considered at the arc circle, you see, because you see at each of the segment there is a small arc, and for that you can simply go for the d theta, and whatever the deflection will come, that is equals to x d theta. So you see here, with that consideration, you simply go that okay, we have a dx small segment where the small deflection is there of delta. So with that you see if we are talking about the total distance bb dash, then we have the delta is equals to integration of a to b x into theta, because you see what we are doing here, we are going for a small segment where the d theta this segment is there and the distance is x. So now once you have this particular segment, this like x into d theta, just take the small like the deformation for this, integrate for entire section, you have the total deformation for that. So with that you see like what we can do here, simply put those limits a and b between those particular portion, and we can simply substitute that value into the main equation d theta, which is m dx by this ei. So if we are keeping those conditions there, what we have the deflection term, this delta is equals to a to b x times you see this one is there m dx divided by ei, or we have this deflection delta is nothing but equals to a to b m dx ei m dx divided by ei into x. So now you see here you have two main equation, one is the theta equation, so theta is equals to integration of m dx divided by ei, and you have the delta equation, that is nothing but equals to m dx integration of m dx into ei into x. So you see here now just based on that, whatever the bending moment is coming due to the bending moment diagram is coming due to whatever the load application is there, or whatever the moment is coming, based on that first of all we need to draw the bending moment diagram. Once you have the bending moment diagram, just calculate that whatever the area is there for that, and based on that you can simply get the value of either the theta or this or we can say that we can get the value of deflection delta. Since m into dx, as I told you, the area of the shaded strip of the bending moment diagram, and x is the distance from B, this particular distance, the x is the distance of that particular thing, and we have the bending moment diagram. Therefore, we can conclude that the right hand side of the above equation, this from this one side, you see here, just in corresponding way. Right hand side of the above equation represent the first moment area that with respect to B, and the total bending moment area between A and B is always divided by EI, so that whatever the flexural rigidity is coming due to this load application, it can be easily incorporated in those deflection term. Therefore, we are in a position to state above condition in form of the theorem, which is nothing but is equals to this, that the deflection of any point at any point, we are taking here the B point, because you see we are taking the distance from point B in relation to the point A is nothing but equals to 1 by EI, the first moment area you see with respect to the point B of a total bending moment. So what we are doing here in the first case, where you see we want to take the slope is nothing but equals to 1 by EI, the total bending moment area, you see only just whatever the area is there. But here you see if you want to calculate the deflection, because you see in that case what we have done, you see the delta was nothing but equals to m into this m into dx divided by EI into the x was there. So now you see it converted into the first moment of area. So you see here the second theorem says that if you want to calculate the deflection for any point, you can simply go within those limit region, and then you can keep those values there. So we have 1 by EI into first moment of area with respect to the point B of the total bending moment diagram. Further, the first moment area according to the definition of a centroid, because you see where the O point was there, and we simply located the O point in the this bending moment diagram, which gives you the centroid and which has a distance of x bar. So with the definition of the centroid, it can be written as delta A is nothing but equals to 1 by EI into A into x bar. So x bar is, you see what it is the location from you see the one region, like you see if you are talking about the this right hand region or the left hand region, from one region where you see all of the center of mass is concentrating. So with that you see like always it is coming in terms of the x bar, because we are flowing with the longitudinal axis, so x bar is there, where ax bar in this you see where the delta A, if you want to calculate at a certain position of the deflection. So if you are talking about the deflection at point A, which concludes that it is ax bar divided by ei, and this ax bar is nothing but the like the distance of the centered x bar, and you see A is the total like area of a bending moment. So we need to calculate that what will be the total area of the bending moment is after keeping those total bending moment area in that. Again you see we need to locate that where the center this centroid position is. Once you have the centroid position, once you have the area, once you have like once you know that which material of the beam is there and what is the cross sectional area is there, you can simply get the deflection at any kind of beam. Or whatever the kind of loading is. So with the deflection term you see which we describe like in terms of the centroidal part, that if we have a centroid in this particular beam, like the bending moment, we can simply calculate this like the delta A, which we discussed is nothing but equals to ax bar divided by this ei. Therefore the first moment of area may be like obtained simply as a product of the total area of the bending moment between like the some such certain point, and then we need to multiply with the distance to its centroid x bar. So once you have like this kind of the first moment of area and you have the x bar distance, we can easily calculate the slope at any like, or we can say the deflection at any point. And if there is exist any inflection point or point of contraflexion, that means you see if that is a special case is there, that if bending moment is changing from sagging to hogging position, or if there is like the change is there from plus to minus, in that case we have a point of contraflexure for an elastic line of loaded beam between any point. Then you see we need to go for a different section, like you can see here on your screen. There is like we have a section that O to B is there, and in between you see if this kind of like the deflection curve is there and a curve is there, and then you see if we are putting the tangent on this particular part, and if we have like this kind of abrupt change is there in this. So for these things, if you are going for the bending moment, then you have like for this section we have the bending moment positive, and for this section we have the bending moment this negative. So with that you see we have a point of contraflexure. So if this condition is there, then what we need to do, then like the adequate precautions must be exercised in using of like the above theorem, because here you see there is a change in the area abruptly you see from positive to negative, and in such a case the bending moment diagram gets divided into the two portion, positive and the negative, as we shown in the previous diagram. And then you see we need to take the corresponding centroidal part from the different references, like C1 for positive, C2 for positive, and then you see we need to write like the slope equation for different segments. So here you see like as I told you, like we are dividing into two different sections. So for that we need to describe like for A to 0, like the O position is there, and if it is going for A, so for that section we have a positive bending moment. So for that we have A to O m dx by ei, and then you see for like from O to B, where you see like the abrupt change was there, the hogging part is there. So for that O to B m dx by ei, and then like again the same procedure which we need to follow for the deflection part, that like once we have the slope, even we can go for the similar way, that A to O m dx by ei into x minus this B to O you see m dx ei into x. So what is the relative changes are there as far as the slope and the deflections are concerned. We need to incorporate those changes in those equations, and we can get a real feeling about that how the bending moment and how like the shearing will occur in those things under the deflection part. So you see here this was a pretty special case when the point of contraflexure was there, and in that case you see we are dividing the beam into two different segments, in the positive as well as the negative like the bending moment, because you see we are simply focusing on the bending moment diagram. So you see here when we have a positive bending moment diagram, when we have a negative positive this negative bending moment diagram, then we need to consider accordingly, and we need to incorporate those sign convention in calculation of the slope as well as the deflection. So now you see here whatever we discussed, the area moment method, now we would like to apply on certain like the example this conditions, and it is coming in terms of the example. So here you see the example one is we have a cantilever beam which is subjected to a concentrated load as we discussed in the first case, at free end, it is pretty easy, you know, like it is required to find out the deflection at the free end for a cantilever beam with using of the area moment method. So you see here, because we have already discussed about this cantilever beam free, you know, like at free end we have this point load is there, or concentrated load is there, and we calculated with the using of direct integration method. But here you see we need to calculate the deflection with the using of area moment method. So for that, again, as I told you, you see all the focus is there on a bending moment diagram, because it is a semi graphical method. So first we need to calculate the bending moment diagram for that. So here on your screen you see you have straight this cantilever beam, point load is there, and the total length is L. So for that we have a bending moment diagram here. So WL is the maximum bending moment, which is there at this, and here you see, you know, like we have a 0. So starting from that, since a point load is there, so there is no like the curvature path or parabolic path, a straight line is there. So if you go with this particular section, we have a triangular shape is there of a bending moment diagram, and if you want to locate the centroidal part, this centroid, then it is always, since it is a triangular part, so 2/3 of the distance will give you the centroid. So it is 2L by 3, at which the location the location of the centroid is located in this particular diagram. So you see here we have the required information in that sense. Now you see we can simply work out the problem in terms of the 0 condition slope to the maximum slope condition. So for that, slope at point A, the initial point A, is nothing but equals to 1 by EI, which is the flexural rigidity into the area of bending moment between those points A and B. So with that, you see, you know, like what we have, you know, like 1 by EI. Now what will be the area? It's a triangular area, so half into the width half into the distance into the height. So you see here half into L into WL, which is the total height due to bending moment. Keeping those conditions, we have WL square divided by 2 EI. So the deflection at point A, which relative to point B, may be, you know, like again obtained by applying the second area moment of theorem. You see where we can simply get the deflection term. So you see the deflection, you know, like is nothing but equals to 1 by EI into, you know, like the first moment of area of the bending moment diagram in between those points A and B. So after keeping those conditions, what we have 1 by EI into AY bar. So you see here we have a triangular element. In that, you see we can simply calculate the area as we calculated, which is nothing but equals to 1 by 2 the distance, this is L, into the height, that is WL, and then you see this AY, the Y bar is nothing but the location of the centroid from that point. So you see here, since it is a triangular element and it's a uniform triangular part is there, so it is 2/3 of the distance. So by keeping those values here, what we have 1 by EI into half of L into WL into 2/3 of L. So by keeping those values, we have WL cube by 3 EI. So you see here, you know, like it's in comparison to the previous method, it's a very simple method, no boundary condition. Straight away, once you have a feeling of the bending moment diagram, you can simply have the slope as well as the deflection. So this was a pretty simple path. Then if you are going for the next you know, like example in which a simply supported beam is there, and in the simply supported beam we have a point load at the mid span of this, and we just want to find out the deflection. So here you see, you know, like at A and B, these are, you know, like the rigid supports, and at these particular pin points are there, and at these pin points we have the reaction forces, and due to that, you see we have, you know, like the point load is there. Due to that, we have the deflection which is maximum at the center point. So now if we are drawing the bending moment diagram for this, we have, you know, like straight way at these 2 points there is no, you know, like the bending moment. Here it's a maximum bending moment at this particular point. So we have a clear triangular part is there, and this height is nothing but equals to WL by 4. And then you see, you know, like now we want to find it out that where the the location of these centroid is. So centroid is located at, since it is L by 2, this distance is L by 2 because it's the total L. So in that, you see the 2/3 distance, so 2/3 of L by 2. So we have, you know, like this L by 3 distance is there where the centroid is located. So now you see we have 2 different triangles in the sense that they have a symmetricity in terms of their height WL by 4, in terms of their base they have the symmetricity, and then you see since it is a symmetrical triangular part, we can simply go for the location of the centroid, which is the 2/3 of the distance of this. Since it is distance is L by 2, so we have 2/3 of L by 2, that means L by 3. So now with the remembering all these things, now we would like to calculate the slope and the deflection for this kind of thing. So for that, you see slope at point A is nothing but equals to 1 by EI area of the bending moment diagram between the A and point C. So now by keeping those things, what we have 1 by EI into half into L by 2 into WL by 4, because you see half the area, you see half into the total this length, this is L by 2 and this is height WL by 4. So by taking those things, we can simply go for the half of the area, because you see for half of the cylinder, for half of the this rectangular part, we have this kind of thing. So the total for in between the point A and C will be equals to WL square by 16 EI. And you see the similarly we can also calculate the deflection part in between the point A and C, and which can be easily calculated by the same theorem 2, 1 by EI into the first moment of area of the bending moment between point A and C. So by keeping those things, again you see we know the area, which is nothing but equals to half L by 2 into WL by 4. So this is one area, and then we know the location of the centroid, that was nothing but equals to 2/3 of distance, that is L by 2. So you see here, and if you are going for the entire this triangle, then you see it is this 2/3 of the total distance L. So now you see by keeping those values here, what we have this delta C is nothing but equals to 1 by EI half L by 2 WL by 4. This is the total, all those elements are calculating for the area, and then you see this Y bar is there, which is nothing but equal to 2/3 of length. So you see for the entire region of this beam, where you see the bending moment diagram is like that, you see here the deflection is nothing but equals to WL cube by 48 EI, and also you see we calculated in the by using direct integration method, we calculate the same thing. But you see, if you remember that part, it was a real the bulky equations was there, then you see we put the certain conditions to get those values. So but here you see it is pretty easy to calculate by simply going with the this bending moment area and the first moment of area for this particular bending moment. So you see here, in these two examples, the loading was pretty simple. That is the main constraint for this kind of thing, that loading must be simple so that we can get a straight feeling about the bending moment diagram, and then we can calculate. So here in the third example also, which is the last example, again we have a simply supported beam. Instead of point load at the mid span, here we have a UDL. So with that, you see we have this shear forces, and we have the bending moment diagram. So in that, if you are calculating this, if you focus on the bending moment, then we have the bending moment maximum is nothing but equals to WL square by 8, which is exactly at the center position. And then you see this distance is nothing but equals to this L by 2, because this is the total length here. So for that, you see, if always you see when it is a curvature, the parabolic path is there, the centroid is different, because you see in the the triangular element we had a centroid at 2/3 location, but here you see we have the centroidal part exactly at the 5 by 8, means 5 by 8 into whatever the distance is there where the centroid is locating. So now you see we have a circular element, this parabolic element is there in this way bending moment diagram, and we have the distances through which we can calculate the centroid. So by keeping those things here, we can simply go for the slope as well as the deflection. So slope is nothing but equals to 1 by EI into the area. So again you see it is the area where the 2/3 into the main the total height is there, which is WL square by 8 into you see the L by 2, the total distance. So this and this once you can simply go for the this area. So once you have this area, once have the structure properly, you can calculate the slope. So here the slope for this simply supported beam under the UDL is WL cube by 24 EI. And similarly, you see we can calculate the deflection, which is nothing but equals to 1 by EI into A Y bar. Y bar, you see we already put those, that 5 by 8 into L by 2 is there. So by keeping those values, we have 5 by 384 EI into WL4. So you see here the same conditions these for deflection at point C, the maximum deflection or maximum slope we observed by the direct integration method, but that method was very complicated, the bulky equations was there. So it's better that if we have a simple loading condition with the simple bending moment diagram, it's always go for the area moment method instead of direct integration method, because it always reduces the computational time, as well as it gives you a semi-graphical method, so you have a clear feeling about the distribution of these bending or the deflection in the entire beam under the loading condition. So in this, like the chapter, we discussed about the main method, the alternative method, that is the area moment method, like, and then you see we found that like it's pretty easy to calculate the slope as well as the deflection based on the bending moment diagram, and you see the first moment of area once you have the bending moment. So now you see in the next lecture, you see we are going to focus on the different method like Macaulay method and the energy method, so that you see we just want to have a feeling that instead of these methods, which method is applicable in which conditions, so that you see if we have a different kind of problems, we can straightly go with the different kind of methods which are suitable method for solution. Thank you.
Thank you.